So let's get started, everyone. So today we're going to we're starting a new section in class. So on clustering. For those of you here, at least. So if not, hopefully so you're watching online. We'll have 4 lectures on clustering. The first one will kind of try and define what is kind of the main motivation of clustering and kind of some basic things to kind of look for in clustering. And then so then we'll also talk about kind of hierarchical agglomerative clustering and density-based clustering as 2 approaches within this. If you are looking at the so at the schedule, then we're going to have 4 lectures. Next one will be on k-means and assignment-based clustering. Then we'll look at spectral clustering, which represents the problem as a graph. And then this year I've added a lecture on choosing K. K is often the number of clusters you have. Added this because I find a lot of people end up doing projects on the clustering. I'm not a huge fan of clustering as a useful thing to actually do with your data. I think it's sometimes helpful, but not as much as you might think it would be without having actually tried it out on some actual real raw data. But I want to add another lecture on this. And the question I always get asked is like, and we never have time to discuss in the classes, how do you choose the number of clusters? So there'll be kind of a lecture on this and the different perspectives here. Again, there's not going to be one perfect answer, but we'll give you kind of several ways you can choose from here and kind of which one is appropriate. So the other thing I'll mention is I am going to be traveling next week. So I have some guest lecturers, people coming in to give the lectures. On Monday will be my PhD student who used to be used to be a professor before he joined the PhD program here. So he's taught before. So I think, and he worked on graph theory before. So I think he'll be able to give a very good lecture on spectral clustering. And then the one on choosing K will be by Dr. Rezig, who teaches the foundation of data analysis and other kind of classes related to this. So I'll have other lectures. We will probably, I don't plan to record those lectures. So if you are not able to make it, you'll be able to see the notes, but if you want to see the lecture, you have to actually come here physically into class. Okay, and then we'll come back and there'll be a clustering homework. I'll try and, it's mostly ready. I'll hopefully have it out by Wednesday, if not at some point this week. It's not due till kind of the end of the month. And then we'll start on the streaming and kind of time series perspective kind of analysis. Okay, the similarity homework. How many people have started on this now? It's due on Wednesday. Okay, a few of you many of you have not started, it looks like. I don't know. I hope it's good practice for this assignment or for this area and useful things to get experience doing. Again, if you have trouble with installing the software, the office hours for the TA will be today at it's 3:30 today and also tomorrow. So if you have questions on that, you can go check in with the TA. Yeah.
I think it's the last part of 2.
Yep.
Group 4. So we're still using the vectorized format since I use face.
Yeah.
I still use that to do all those calculations.
So once you have the vectorized representation, you don't need to do it through face, right? You have all the data as these 100 1,000-dimensional, these vectors in 100 dimensions, right? And you just need to write a for loop to go over those. Kind of, I want to demonstrate the speed up that you're getting by not doing brute force. Okay. And so I believe it should be substantial. Yeah, the brute force, if you have a slow computer, this might be kind of slow to do. Or if you don't, if you're doing in Python, suggest trying to do what's the method to kind of do a kind of compiler within Python? Because it's procedural, so it'll walk through the for loop slowly. But there are ways to speed up your Python code with there's this one line, I'm blanking on it now, that's kind of tells it to kind of try and pre-compile before it runs. Anyone remember when? So okay, if it's too slow, or I remember, I'll try and post this on Canvas. This may speed up this sort of computation kind of significantly. But it should still be slower than using face or something else. Did you have trouble installing face, or it was okay?
I just used it. So
Yeah.
Face dash.
Great. I think if you have kind of Conda already installed, it should be very straightforward. And if you haven't played with a lot of this stuff yet, then that's where it might be challenging doing it for the first time. Yeah, okay. Well, and then this last question we haven't talked about yet. This is kind of based on the locality sensitive hashing approach, kind of just doing this angular similarity kind of hashes. How many of these of these kind of 1-bit kind of representatives of the similarity do you need to get good to measure the similarity well, right? So just kind of explore with this. It's a pretty straightforward thing to calculate, but just a little exploration on that. All right, any questions on the homework? If you do, if you get stuck, the TA has office hours today and tomorrow. So, all right. Well, then let's get started on clustering. All right. So, kind of, I'll say clustering is about, and I'll say this more kind of mathematically in a second, but it's about taking a data set and trying to group together similar kind of similar objects. So similar objects are in the same cluster, different objects are in different cluster, and kind of adding some structure to your data. Oh, and just since about 5 or 10 people have joined since we started, next week I'm traveling. I have some people coming to give the guest lecture, but I won't be here, and we probably will not record the lecture. So good idea to come to class, especially. All right, so we're trying to group things together, and so kind of a general rule I just want to write up here. When data is well clusterable, there's like well-defined groups of data with respect to the way you measure the distance, then most clustering algorithms formulations just work well. It's not going to matter which one you choose. And when data is not well clusterable, so the data, there aren't like well-defined subsets of the data into groups, then it doesn't matter what algorithm you use, you're not going to be able to magically find clusters. All right, so what we'll be talking about a variety of algorithms in the class, and formulations, and we'll talk about the most popular ones, give you a sense. And the differences between them are kind of on the edge, right? If things are really well defined, you could use any of them and you should probably get about the same result. If they're not well defined and things are not really grouped in clusters, then there's nothing you can do. You can't magically create clusters out of the data. And what we'll see is there's not some one notion of what is the best way to do it either. There are many kind of possible options to do. So to kind of to say this a bit more, for clustering, okay, we're going to assume that the input is going to consist of three things. It's going to consist of the data. We'll say this X, and this will be a subset of some space. Okay, I'll say the space is M, and probably this will be equal to RD. So some d-dimensional space, but it could be other objects. These could be sets or something, or it could be raw data like images or text or something else that you're working with for your projects. We will assume as input a distance, okay? So it'd be a distance function defined between, as a bivariate kind of function, takes in two elements of the space and produces a real value greater or equal than 0. And we will have some parameter, okay? And this will be e.g. the number of clusters K. So the algorithms we talk about today will typically have a different, some will have a different types of parameters other than just the number of clusters. So the density-based clustering will have some other parameters, but changing those will change the ultimate number of clusters. And so kind of, you could change those parameters and see how many clusters you get. And ultimately, you'll get something like the number of clusters as part of the input. All right. So, and then, as I mentioned, the second lecture next week, we'll talk about how do we choose this. Okay. So, but we're still given as input the data and the distance of how we measure how close two things are in the space. It is definitely the case that if you change the distance function, or for instance, you take your raw data and you featureize it into a very different way, so the natural way to measure distance between them changes, you can get very different clusterings. In some data sets, this can go from not finding any structure at all to finding a lot of really nice, sort of well-defined structure. And so this choice of the distance, right? This is a choice. Okay, so this is a choice. And so that will really influence the algorithm, probably much more than how you define the kind of which algorithm you actually choose to use. Okay, so it's why we spent a lot of time talking about distances and stuff before we got started into this part of the class. So we'll probably typically use the Euclidean distance as kind of the representative one. I'd like to draw pictures, and then the straight line distance is the Euclidean distance. So this will probably be what we talk about. A lot of these things will be interchangeable. I can plug in any distance I want. Sometimes it will need to be a metric distance. Sometimes it's not really going to, it's not going to care. Okay, so this is kind of the input to clustering. Okay, and then what is it we want to be doing? Well, a clustering will look like the output is going to be a set, kind of a, what did I write this in my notes? A clustering of X will look like a set, S1, S2, up to SK, right? So these is going to be a set of clusters. And if we specify a K parameter, there will always be K of them. Okay, and what properties do these have? Well, so we're going to have that each Sj will be a subset of our input data, right? So we'll think of having a set of points. Ideally, it will look something like this, right? This is our data set X, and then this may be S1, all the points inside the circle will be the first clustering. So this set of points will be the first clustering. Okay, this will be one property we have. We will typically say that each pair Sj intersect Sj prime, this is going to be empty set. Okay, so this is for J not equal to J prime. So if I have two different clusters, this is S1, this is S2, there's no overlap between these. This in particular is the hard clustering. Okay, so hard clustering enforces that the clusters do not overlap. There's something called soft clustering, which would allow this. We aren't going to talk too much about soft clustering in this class, maybe in the last lecture. So, and then kind of we'll also say that the union of J equals 1 up to K of Sj is going to be equal to the whole set. So that means this is going to be a partition of the data. So this would be S3, S1, S2, S3, and that includes all the data. Every data point is in at least one of the clusters we have identified. Okay, so these subsets would be called the clusters. This would be called a cluster. Okay, and so sometimes so you might not put some points inside of some of the clusters. For instance, if you had one data point out here, so you have 3 well-defined blobs, and then you have a data point far away from everything else, you might say this is an outlier. And so then I'm not going to assign this guy into any of the clusters. So maybe you can do that. We will see. Yeah, so some algorithm today that is kind of useful for identifying outliers, and we'll talk about outliers kind of later on in the semester after fall break a bit. So as well. So okay. So I've told you what the structure of the output is. I haven't told you what's a good clustering and what's not a good clustering yet, but we've actually already run our first clustering algorithm. You probably won't find this in most textbooks, but I would say my recommendation for your first clustering algorithm to run is to plot the points and then circle the clusters. Okay, I'm totally serious. I actually think this is what you should do. If you think you might have clusters and your points are in 2D, you should do a scatter plot, and if you think that Euclidean distance makes sense, then you should try and circle them so that the group points are there, and draw a circle on them, right? This is going to work as well as any other algorithm. Again, if the data is well clusterable, then this will work well. If it's not well clusterable, there's probably nothing you can do. So if your data is in 2D, plot it and draw circles around the groups of points. It's hard to go wrong with this. It feels less automated, but as we'll see, there are lots of choices here, and you kind of don't know what's the right formulation to use. And so you probably want to plot your data to kind of do a sanity check that it's not doing something really silly. And once you do that, you might as well just circle the answers. Okay, if your data is not in 2 dimensions, well, we'll see later, you can use dimensionality reduction to project them to 2D. And so this is, again, an algorithm that you can use. With dimensionality reduction, there'll be some caveats, which we'll talk about when we get to those parts of the course. Okay, but this is our first algorithm. Okay. Does anyone not believe me? I actually advocate for this. Okay, I'm completely serious. If you do this for your project, I will ask you if you tried running this algorithm. And if you didn't, you probably are trying to automate it too much and not thinking about the problem. You should be checking these sort of things. And when you can draw pictures and plots stuff, you should definitely do that. Okay. Okay, but we could probably stop here. And this will solve the problem 50% of the time that you have interesting cases. Not very satisfying, so let's keep going, add some more mathematical formulations, see some different methods, and yeah. So I have some lectures to fill. Okay, all right. Okay, so what makes a good clustering? Okay, what good clustering? Okay, and we're going to kind of see through the formulation of algorithms a bunch of different answers to this. A lot of times, what people decide makes a good clustering, they kind of rationalize it after they choose what algorithm they want to run. They said, I want to run this algorithm. And they say, well, why? What was this algorithm good at doing and finding? And then they'll say, well, that's what I mean was a good clustering, because that's the algorithm I actually wanted to run. Right? Okay, so let me try and abstract some of this notion. And so kind of say that, again, we'll say that our data might look like this. Okay, and so we're going to kind of quantify this with two properties. So the width, okay, and so this will be something about the variation within a cluster. So this is for each kind of cluster Sj. I want to say for points x prime that are in the cluster Sj, then I want the distance x prime to be small. Okay, so I want this to be small. So think of within a cluster, I want to look at these distances between x and x prime, right? And there's lots of distances I can measure, but I want to look at these distances, and I want this to be kind of the width of the cluster, somehow a measure of the distances within the cluster, and I want these to be small, right? X prime, right? So this is these 2 points, but I can measure all kind of any pair of distances here. Okay, so I can, and how do I, and there are lots of ways I could turn this into a single number, right? I could look at the longest distance, I could look at the average distance, I could look at the median distance, I can pick one point and look at the average distances from that one point. There are lots of ways I can formalize this notion of width. And we will formalize it in a bunch of different ways. I'm not going to do it yet. Okay. Okay. Another thing we care about is the split. Okay. So this is for Sj and Sj prime. So for two clusters, then for most kind of x in Sj and x prime in Sj prime, then I want the distance between x and x prime to be large. Okay, so that would be that if I look at the distance between these two clusters, or I can look at all these distances, right? This is a point x, and this is a point x prime. This would be from Sj prime, and this is Sj. Then this notion is called the split. I want this to be large. So two clusters, I want the distance between them somehow to be far apart. And I can, again, quantify this by measuring the distance between pairs of points. Okay. Okay, again, what do I care about here? Do I care about the minimum distance, the maximum distance, the average distance, the distance between representative points? These are all valid options we could be thinking about here. There are statistical formulations. I can say, I can fit a probability distribution to each of the clusters. And then I could say, what's the probability that one of these points from another cluster fell in was modeled well by the first cluster. I can do something like that too, right? I can put more and more structure on this if I want to. Okay, and then kind of overall, we want something like width minus split, or maybe say width divided by split. I want something like this to be large. Okay? Oh, small, right? I want this to be small. Okay, so, or sometimes I just measure something like the average width, or sometimes I do something that has to do with split. Sometimes I combine them together. Okay, there are lots of formulations here. Okay, you can start to get the idea of that there are lots of ways I can mix and match these things to get some form of talking about the clustering. And which one's the right answer? Right, so if we're doing a classification problem or something in supervised machine learning, right, what we can do is we can take the data set and split it into a training set. We can run algorithm on, we can evaluate it on the test set, and we can run a bunch of different options and see which one does better on the test set, right? It's not as clear how to do that here, okay? There's not a way to kind of do this test train split cross-validation trick to compare which one is better. And so people write hundreds and hundreds of papers on this, each claiming their method is the right way to do it, and other ways are the wrong way to do it. And people can fight and argue with each other all they want. And there's not kind of like a resolution on which is the one best way to formulate it and the best algorithm for this. So what do you think? So how do you think people choose which formulation to do, which algorithms to run? Yeah, so which one is the most efficient, right? I want something that tends to give me answers that look good when I plot them, right? That should make sense when I plot them, and it should be efficient, right? So things that make sense when I do some sanity checks and I can run efficiently, or is at least is easy to run. A lot of this is the literature is fairly old and predates kind of desktop computers at least, and so it was also kind of how easy was it to actually implement and describe what to do. I think that this was also a factor when this field was kind of got going. So there are a lot of these other aspects that kind of went into it. All right, yeah.
Last semester, I took a machine learning class and we used k-means. One of the ways to find the k we used, it was called like the elbow method.
Yep, okay.
I can't remember how it was implemented. We weren't asked to implement it, but we used it to find the right k to get the right number of clusters.
Yep, we will have the fourth lecture. The lecture next week, Wednesday, will be all about choosing the number of clusters and how do we choose that. And one of the methods we'll talk about is going to be the elbow method. Yep, that makes, yep. So that's one of the methods, either very satisfying or not very satisfying, depending on your perspective on it. Yep, and so k-means will be what we talk about on Wednesday. Okay, and the family of approaches like that. Okay, so today there's another aspect that you might want to why you want to choose a clustering method or formulation is that it might give you a little bit more structure, and so what we're going to talk about kind of today in this context is hierarchical agglomerative clustering, okay, HAC. And so this family of methods is not particularly efficient. The last part of this lecture, we'll talk about kind of something that does something like this that's more efficient. but this adds extra structure. In particular, the hierarchy is going to not provide one clustering, but it's going to provide naturally a hierarchy of clusterings. And so this additional structure is sometimes interesting. However, at the same point, it's going to be less efficient. And there's not as much mathematical kind of perspective on this approach. It's kind of people came up, said, this is a natural algorithm to use. So I'm going to run this method and then we'll see what comes out. And then the people afterwards tried to rationalize why this was maybe a useful thing to do to mixed effects. So this family of things are basically going to follow the premise. If two kind of clusters are close, then I'm going to merge them into a single cluster. Okay, and the clusters initially will just be points, right? Individual data points. Okay, so the algorithm HAC is going to be as follows. So initialize. So I'm going to put each xi and x in its own cluster Si. So after step 0, if I have n data points, I have n clusters. Every point is in a cluster of size 1. Okay. And then I'm going to have a while loop. Okay. And while two clusters are close enough. Okay, while two clusters are close enough, then I'm going to find the closest pair Si and Sj, and I'm going to merge Si and Sj into a single cluster, S prime, which is going to be Si union Sj. Okay, so this is the algorithm. Okay, so it seems a fairly natural thing to do. I'm going to have a bunch of points, and if 2 points are close enough, I'm going to merge them together. Then later, if I think 2 clusters are too close to each other, I'm going to merge them together. And I'm going to keep doing, always finding the closest pair of the clusters to merge those first. Okay, and I repeat this until clusters are close enough, are not close enough anymore, and then I will stop. Right, when I don't think clusters are close enough, then I will stop. And so maybe when I have k clusters, I will stop if that's my parameter. Yeah.
So let's say a cluster is a combination of two, what used to be 2 clusters, 2 points now. Which of those 2 points would you measure the distance between that cluster and another, or would you take the mean?
Great question. Great. So I haven't defined yet a couple of things yet, and I haven't defined how do I define the closest pair of clusters, and then how do I choose I need to define some notion of close enough. Okay, so I haven't yet specified this yet. I have to somehow say I have 2 clusters, which could be not individual points. If in that case, we know how to define a distance, but if I have 2 point sets, how do I measure the distance between those 2 point sets to say that the clusters should be merged together? Those are the closest 2 clusters. And there are a variety of ways I could define this. Okay, and depending on that choice, it's going to give you a different algorithm. And this is a case where you will see some fairly different sorts of structures. This is kind of give you the most deviation from the thing I wrote on the first slide, that if they're clusterable, you will always find it independent of the algorithm. This can give some fairly different sort of structures. to mixed effect, that you can depend whether you, the most famous version we'll see called single link, I think sometimes gives some very weird structures that I think are, you guys will decide with me during the lecture whether you think that's a useful thing to do. All right, so yeah, so I am missing this question, how to define this question to find the closest pair, or in particular, how do I define close between a pair of points, right? And so specifying this, I want to find a distance between S1, let's call this, or like an S and S prime, where S and S prime are both subsets of X. Okay, so I could have, so this is S, and this is S prime over here. How do I, and maybe I've write this one in blue, so it's a little bit different. How do I measure the difference, the distance between these two sets of points? All right, so you had some ideas. How should I measure, what are options I should consider? So I can take the mean of all points in S, or in S prime, or in the,
for each point, you can take the mean within that set, make that be, it will kind of come to like a center point, and do that for all sets, and then measure the distance between those 2 points.
yeah, okay. So let's write this down as an option. So option 1. Okay, so I'm going to say mu is going to be the mean of S. Mu prime is going to be the mean of S prime. And then distance between S and S prime is going to be the distance between mu and mu prime. Okay, great. So this could be, for instance, I could take these 2 points and then I could draw the distance in between them. And this could give me a distance between the 2 clusters. Great. This is a reasonable choice. What are other options? Yep.
Maybe you could like sum the distance between all the points between each set, and then you divide that by the amount of points in each set.
Okay, right. So I'm going to, okay, so let me write down what you said. So I'm going to say 1 over, for all the points, X in S, then I'm going to measure X minus, 1 over S prime, X prime in S prime, let me actually just write it this way. So I can do now the distance between X and X prime, right? So it's the average. So I've averaged over all the points in X and average over all the points in S prime, the distance here, right? And in fact, I can pull out, I think any way I write this, I can pull out this factor, and then I sum over all the points X in S, X prime and S prime. Just measure it like this. So this would be the average distance, but weighted by the number of points in each of the clusters. Okay, and it turns this is just going to end up being the average distance among all pairs of points. So this will factor out here, and I will get this term here, right? So this is kind of the average cost, the average distance between all the points. Okay. Yep, this is a reasonable way to do it. Okay, we haven't hit on the two most common ways yet to do it under this HAC formulation. What are other ideas?
Something similar to mean, but with median, go through each feature, take the median for each feature in the set. That way, if, let's say there's some noise or there's a big outlier, it can be ignored.
Yeah, how do I define, so even if I'm in 2 dimensions, how do I define a multi-dimensional mean? Do I want to take the coordinate-wise mean? So there are multiple ways. So how to generalize the median? The median is kind of robust to kind of outliers in a certain way that the mean is not, right? But how do I define the mean to multi-dimensions? The point that minimizes the Euclidean distance of the so if I take the coordinate-wise mean, what that does is it minimizes the sum of the squared distances to that point. And if I do the coordinate-wise mean, I get the sum of the squared Euclidean distances, even if I do it by coordinate. But with median, I don't get this property. I could do something like find the point that minimizes the sum of the distances. This would be called the geometric median, or and we'll talk about this version, this kind of thing next lecture. But I could replace this mean by some other representative, right? I could say that mu is a representative of S, and mu prime is kind of be a representative of S prime. For instance, it could be I've taken the minimum enclosing ball of this point set, and then I pick the center of that minimum enclosing ball. Okay, that's another option, right? Or the smallest ball that contains 50% of the points. That might be robust outliers. Turns out it's pretty robust, right? So there are lots of ways I can take a representative point and take the difference between them. These are all valid options. Yeah. Great, so this will approximate using this one, right? And if I take the mean of the random points, it will approximate this, right? And you can use kind of concentration bounds that you may have seen in other classes. We won't review them here, to show how well they approximate these two measures. Those are reasonable things to do, and they would be more efficient than this. This one's actually not too inefficient. I can pre-compute the means, right? And then I can just replace them. If I use the squared distance here instead, I think this will actually give me the same answer in the ranking order of which clusters are close to each other. Okay, so that'd be there's going to be, I can factor out some of the computation here, and I can write it as the distance to the means plus some constant terms. I think if it's the squared distance here, I forget which one. But so there are ways to speed this calculation up and pre-process some aspects of it. If I don't care about the distance itself, but I care about kind of which one is the closest, which is just maybe all I need here, but the close enough, I may need to use the actual distance. Okay, we haven't hit on the most common things within this framework. Yeah.
Use something like SVM for a margin, and we can find the min or the max of the pair of S1 and S prime. And if you compare the minimum distance, you don't have to compare everything. You just make that a threshold.
Yeah, so you're saying, let's say we found the max margin separator between these 2 point sets, and that means that if I drew this right, there's some separating region between here. And what I actually care about, this is kind of a max margin. What is the length of the margin? it's not the same. Okay, so the margin might be defined by 1 point here and 2 points out here, but there might be no points in this region here, right? Let me draw a separate picture here. That's a good question, right? But the margin can be defined like this, but the minimum distance is this, and this is the margin between them. So those aren't exactly the same. But it's a good question. I could use the margin, the margin between the two point sets. What is more common to do is the minimum distance. Okay, I'm going to say that the distance between S and S prime is equal to the min over X in S, X prime and S prime. Okay, just look at the minimum distance between the points. Any pair of points, I want to find how small could it be. Okay, this is called single link. Single link clustering. Okay, and then there's another one that's kind of like this that I will write up here as the other most common one. S and S prime. Replace this with the max. And this is called complete link. Okay, so complete link is going to ensure that none of the distances can be too far away when I put things together in one cluster. And the single link just says there's a path where I never have to go too far from one point to the next to complete a path between the 2 points in the cluster. Okay, so if you're thinking about how to group with single link, if I'm thinking about how to group like these metropolitan kind of areas, right? All in like Utah, all these cities connected along the Wasatch Front. Where are the houses on the map? Well, they're all connected. They're very spread out, but from one house to the next house is never that far away, and I can go pretty far along the Wasatch Front, even though some points are very far apart. Where the complete link will force that everything to be close to merge it together, and I might be better to merge here with kind of a Park City area before I merge it with Provo, because Provo is geographically further away, even though there's not a gap between any of the kind of where the houses are. Okay, and so these kind of give different ways of modeling this here. Kind of there are even other ways how to do this. I could say I want to measure the distance based on what if I put them all together, and I want to see what is the average distance to the mean after I put them in one set. Okay, so instead of saying the distance in between the means, I want to say, let's say I added a mean here of all the data points, and then I compute all the distances, and I looked at that score, the average distance to the mean point, and that score tells me how close that cluster is. So another way you could do it, right? We talked about end of last week this Wasserstein distance between 2 point sets. I can measure the distance between 2 point sets with the Wasserstein distance as a way to decide if I should combine these point sets together. Okay, so there are lots and lots of options here, right? Even within this category, the representative point I choose gives me lots and lots of options. All right. Okay. So these approaches are kind of actually more linked together than you would think. Looking at the average link and looking at the mean representative, these are going to give very similar outputs. And it turns out if I want to solve a formulation like this, I probably am not going to use the hierarchical agglomerative approach towards doing it. I'm probably going to use the assignment-based clustering, which we'll talk about, family of k-means, which we'll talk about with the method we will on Wednesday. So these are typically not used in the HAC framework. These two are, because they don't fit as well within the other frameworks. Okay, although, I don't know, this kind of will map to k-center clustering a bit. But so let me kind of give an example. So there's, this, okay, there's this two means, let me, two moons sort of data set. Okay, and I really dislike this data set. It looks something like this as an example of why you'd want to use single link, and like this. So this is the point set, this is X. Okay, and if I use single link clustering, so if I use single link HAC clustering, what's going to happen is I'm going to group this together in one cluster and this together in the other cluster. Okay, because the distance between a pair of points is never too large, right? This is the distance between the points. It's never kind of this. If I even use this fairly small distance between the points, I can completely link together the blue and separately the red cluster, but I have a pretty big gap in between these. If I were to use kind of one of these other formulations, it would not know to keep these points kind of separated from each other. Okay, so this is an example of why people would want to use single link. I like the metropolitan example a bit better. This sort of data set, like this picture, is famous. It's been a lot of different papers and textbooks. Almost never see data that actually looks like this. This is, I do not think, kind of not representative of almost any kind of real data. Okay, so this is kind of the motivation for this single link, but I don't know. This sort of structure is, I think, not super common to actually see. Okay, if you do, you could again solve this by plotting and decide to circle them this way or use single link. But this would kind of be the sort of thing you should have in your mind of what you can get out of this type of clustering. Where if I use complete link, it's not going to give me this. It's going to try and group maybe this together. It might instead say, I'm going to group this together in one set and this together here, or maybe it'll do something like this. Maybe this would be complete link. Might give me 3 clusters instead, but none of the points are too far from here, from each other here, same here and same here. Okay, but the threshold would be much larger, but you tend to get that with complete.
When you have a very large data set, and I mean, you can't visualize this stuff, right? It would be really hard to visualize whether the clustering is being clustered correctly or not.
If it's in 2D, you can plot it. You can do a scatter plot. Yeah, if you can draw the points pretty small. There are lots of pixels on monitors nowadays. When I was in school, like you guys, monitors weren't as good. We didn't have as many pixels, and maybe then you could have argued we can't plot them all. But you guys have lots of nits or whatever they're called on your monitors, and you can plot lots of data points. Okay, and if it's so I don't know. The plotting works pretty well. You can plot it and then zoom in on parts too if you're not sure. It's for 2-dimensional data, it's pretty undefeated. Okay. Okay, let me mention, to be explicitly a bit more, the hierarchy that you get out of here. Okay, so let me kind of run through a small example here. I'm going to think of 1.3. Let's this guy up here a little bit. Okay, so if I'm going to run single link, let's do single link hierarchy. What's going to happen is the first step in my algorithm is going to, so initially they're all their own clusters, and then I'm going to merge these together. So I'm going to think of having 1, 2, 3, 4, 5. And the first thing I'm going to do is this is going to be cluster S1, or we'll call this S6 perhaps, right? It's merged together as the clusters 1, 4, and 5. Then the next thing I would do, I'm going to merge together cluster called this S7. So this is kind of building a hierarchy here. The next thing I would probably merge these two together, 3 and 2. So I would merge this together into a cluster. We'll call this S8. Okay, so now I'm going to kind of build this tree. And then if I wanted to, I want to keep going, I can put this all together into a cluster. We'll call this S9 here. Okay, so now everything is together in one cluster. So I can build this hierarchy over the clusterings. And I could have said, I want to stop when I have 3 clusters, right? So then I chop off the hierarchy with the sets 1 and 2 together in cluster 7, 3 by itself, and 4 and 5 together in cluster 6. If I wanted 2 clusters, well, then I stop when 1, 2, and 3 together are in one cluster and 4 and 5 are in the other cluster. Right, and you can imagine with many more kind of data sets, this kind of gives you some more structure into what's going on here. Sometimes we'll see when we're trying to choose the number of clusters, there may be clusters within clusters, and so there isn't one right answer to how many it should be, and this would kind of give you that structure inside of this. A popular place where this occurs are these phylogenetic trees. Okay, when you're looking at kind of like different animal species, and you're trying to group them together into a hierarchy, and kind of the hierarchy is the reverse order of like evolution when there was a mutation and 2 species split. And so people use this form of clustering in this setting to try and build this kind of this tree, and then you can decide, well, at what level do I want to kind of say, okay, here's a well-defined group and here's another well-defined group. I can decide that afterwards. I don't need to decide it kind of ahead of time. I can just present this whole kind of hierarchy of clusterings all together. And so this is one of the great reasons to use this HAC framework. I don't just give one answer K, I give all the answers at once, and then someone can kind of decide where they want to scope it kind of afterwards. Okay. Okay, so how efficient is HAC? Okay, how efficient is this to run? So I'm going to go, I have kind of n, if I want to build a whole hierarchy, or I stop when there are a constant number, but either way, I have basically n rounds of the while loop, right? So each time I merge a pair of clusters, I have to do that, or I guess I have n minus 1 times. So I basically have linear number of rounds that I have to do the while loop. And then how long does it take to compare? And then within this, I have to compute this J minus J prime, this between a pair of points, but between a pair of point sets. These might be, so they might be kind of so I could have for the first this computation might take O of n squared time if both the size of Sj and Sj prime equals O of n, right? That's the only bound that I have on this. And I may need to compute n squared of these. But you can argue that the total time for the step, but if these are large, then I don't have as many computations to make. And there are kind of, and there are maybe n choose 2 pairs, or on the order, let me say on the order of n squared pairs. So this might take n to the 4th time every step in the worst case. Well, it turns out this step can never be more. It always is a function of all the pairs of distances between points, which I can pre-compute, right? Or I can just look at those distances. Every computation only looks at an n by n matrix of all the distances, and each distance is used in one of those computations. So this whole step inside of here, this all together takes O of n squared time, and this is basically for almost any measure I use. If I use a Wasserstein measure where I have to find the best matching, it could take longer. Okay, but otherwise this internal step takes at most n squared time, because I can just compute that distance matrix and look at every pair of points at most once, and there's at most n squared of those, whether it's a min or a max or an average. Okay, so this would lead to an overall O of n cubed time, okay, which is a lot. Okay, if I use a mean-based approach, if I use if I keep track of, or let's say instead of representative-based approach, representative-based approach, and this was the whole thing in the category 1 of the approaches, then I can get it down to O of n squared times log n, because I only need to recompute the mean on the cluster that I have merged. Once I only have to recompute the one in the merge, and I only have to recompute the distances to all the other ones. The existing clusters, I don't have to recompute the distances between them. And if I'm clever about this with like a priority queue to keep track of the minimum, I can do it in n squared times log n time. Okay, so it can be a little bit faster, but this is actually still kind of slow. I really want to spend near linear time on all of my algorithms. So people don't like these. These are kind of slow for very large data sets. I don't want to spend even n squared, and n cubed is pretty painful. Okay, so these were kind of a popular way to think about clustering and everything, and they gave you this nice structure. But when we got to the era of big data, basically a lot of people stopped looking at these, partially for this reason. Also, I don't think they work any better than kind of the k-means or the spectral approaches that we'll talk about in the next few lectures. Okay, so but one way to look at this is, let's say we wanted to, what is different is the single link clustering will give me something kind of structurally different than all the other approaches we're talking about for the most part. If I do kernel version of spectral clustering, it probably gives me something similar to this. But well, let's ignore that for now. So I want to give something that looks kind of like single link, but doesn't have to do all this iteration that's going to cause these large sort of run times. And so the kind of what the popular output of this turned into what was called density-based clustering. Density-based clustering. Okay, and in particular, we'll talk about an algorithm called DBScan. Okay, and so this is kind of the most popular way of doing this. Around 8 years ago, there was a controversy that the DBScan paper had claimed a certain property of runtime, and another paper from a friend of mine said, not really, that's wrong, even though it had like thousands of citations and kind of fixed it. And they said, it's not really a problem, and here's why. But okay, so let me tell you about this algorithm. So it's given two parameters. Instead of k, it's going to have two parameters. Okay, epsilon, which is going to be a radius of what is close, what is close. This is, and then a parameter, they call it tau, which is min, or they call it min points. And this is a density parameter. Okay, and then here's kind of a picture of how the algorithm works. I'll be a little bit more deliberate in how I draw my point set this time. Okay, so I'm going to start with a radius. This radius will define epsilon, a ball. Okay, and I'm going to kind of think of drawing a ball around every point here. Okay, and I'm going to do this for each point. I'm going to look at a ball around every point and say how many other points are inside this ball. And then I want the density parameter, the min number of points, to say, is it at least tau points inside this ball? Okay, so let's run an example where this is epsilon and tau is going to be equal to 3, including the own point, right? So this circle here has 4 points inside of it, this purple circle here of this radius. The point itself and then 3 other points. Okay, and so if I see that the density parameter is satisfied for this radius, I'm going to mark the point as a core point. So by symmetry, you'll see basically all of these points are core points. And let's say these 3 points are also going to be core points. They're going to have the right amount of density here. I could also draw a ball around kind of this point here, and you see that it's a core point. This one is not a core point, even though it's inside of here, because if I were to draw this ball around this other point, it only has 2 points inside of it. Okay. So now I'm gonna find, so the first step, so I'm gonna find the core points. These are with tau points in ball of radius epsilon. Okay, so I'm going to find the core points, and these were highlighted here. Okay, then I'm going to draw some. So I'm going to draw edges. Okay, and these edges have 2 properties. One is that the distance between a pair of points, x and x prime, is is less than epsilon parameter, the same radius of the ball, and x or x prime is core. Okay, so I need at least one of the 2 points to be core. Okay, so let me draw these edges now. So these edges are going to be, these sets of core points are all going to have edges. So these will have edges. This one will, these two edges will also exist because the distance is less than r, and one of them is a core point. I don't need both to be core points. Okay. I do not draw an edge here. This is not an edge in the graph because their distance is small enough, but they're not both core points. Neither of them is a core point, even though this one is, the one on the left is connected to other core points in the graph, but it's not itself a core point. So this is not an edge. This is not an edge. Okay. Now my clusters are the connected components. Okay, so that two clusters I get out of here. I'm going to get this cluster and this cluster, and these points are going to be not in any cluster. These will be outliers. Okay, the connecting component, 2 points are in the same connecting component if I can walk from one to the other by a sequence of edges. We've seen this definition before. Okay, and so this is the DBScan algorithm. The hard part is I have to mark, I don't have to mark all the edges, like I just have to, I can kind of, to implement this, I actually don't want to mark all the edges. I just want to find the which points are connected to each other. If I have a lot of really dense points together, they're going to be like n squared edges. I don't need to mark them all. Once I know it's connected, okay, I can just realize it's connected instead of marking all the edges inside of a really tight cluster. But I have to be able to do that quickly, and that's where the controversy lied about the runtime of this. But in practice, you can get to run in near linear time, and it gives something like the single link clustering, but would prune really kind of long tails of stuff that wasn't really connected to the core cluster. That wasn't a dense enough cluster. Okay, the algorithm makes sense. It's not too hard to do. Yeah. Yeah, I put the circle centered at each of the data points. Yeah, my drawing was not perfect here. If you look in the notes, I've got a really nice drawing that I made on the computer. But the circles are centered at each of the data points. So I check the circle centered at this data point, how many other data points does it include? That's what defines a core point. So if I have tau points in a ball of radius r centered at that point. Great. So thank you for asking that question. Yeah, okay, so what do these clustering algorithms actually mean, right? So what should we make of the clusters from density-based clustering or single link clustering or complete link clustering? Those are kind of the 3 core algorithms from this lecture that are widely known algorithms. DBScan, single link, and complete link. These are well-known algorithms. You will probably implement, and implement might be running by hand on paper without writing code. That would be fine. You'll implement some of these algorithms in your home. Okay. What do they mean? What should we think of the meaning of these clusters? What do you think we should, how should we interpret these clusters? Yeah, great. Okay, yeah. So if we have supervised learning, we're doing classification, we're given us some points with labels, and we're trying to find a rule to label new points here. In the clustering setting, my input was here, right? It did not, my input was the data set, the distance, and maybe a parameter. It did not include labels. So the clusters, they do give us something like, well, this is one's in cluster 1, I guess label 1, this is label 2, this is label 3. Maybe I don't know what those labels are, but I kind of say, these are all similar to each other and here. So I can kind of interpret them as probably having the same label. And then I can go in and look deeper at these here. Right? So this would be one of the uses of clustering, right? And so this actually does work. There was a project from last semester in this class in the spring when I taught it, and they were working with a kind of one of the students in the class was a junior professor from the health sciences campus, and a group worked on a project, and they've since kind of written a paper where they found clustering in electronic health data. And then they took it to some like physicians that worked on that sort of data, said, oh yeah, these clusters make sense. This class of patients had this property and this property and this property. And it was nice to kind of group them together and kind of see what to make of that, right? And so the fact that they could group them together revealed some sort of patterns that maybe they kind of thought were there, but then it was borne out in the data and they could try and maybe draw different conclusions for the different groups, as opposed to trying to fit a single prediction on all of the data. Okay, so this is one way to do this kind of, the ideal outcome of clustering in general. So I think if that's your goal and you're using single link or complete link, I mean, I don't know if you're going to have a 2 moons data set where this would be what single link or DBScan would both solve this kind of identify these sort of clusters with the right sort of parameters. I'm not sure if I would generalize predictions based on these, but that could be the case, right? If we're looking at metro areas, people who live in the Salt Lake Valley versus up in the Park City area. And if you live up in Park City, you're kind of clustered as you're willing for it to be colder in the winter to be closer to the ski areas. And if you're down here, you're not willing to drive as far, but and maybe the homes are more affordable. So you don't want to have to drive down to where a lot of people work down here every day. And if you maybe you don't go skiing, right? So you might be able to make some generalizations based on how these populations have been segmented from each other. And so clustering allows you to generalize that. And you're trying to do the grouping before you try and fit a pattern onto the data. And this is, I think, really where it's most powerful. And so, okay, so these single link and DBScan will have structure that kind of looks like this. We're going to see a bunch of different algorithms over the next few lectures, and they're going to give different structure on the data. And be good to keep in mind when this would be a good fit and when the other sort of clustering algorithms is going to be a good fit. One of the last thing is there wasn't really a lot of data analysis. We start with some formulation. I say, I want to find the solution, the structure, which optimizes this function, right? A classification has a loss function. I run optimization to find that loss function. As we'll see with a lot of dimensionality reduction or k-means sort of clustering we'll see on Wednesday, we will again have an optimization function, and we will try and solve that optimization function. And the clustering, that output, will be the one that's optimal in some sense. It's not clear what this is optimal for. what would we say is the property we want to optimize to get this clustering? It's a bit harder to think about. Some people have tried to write this down, but it's more, a little bit more convoluted. Okay, and so, and it's retrofitted on the algorithm. People came up with the method, and then later people on said, what was this actually doing? I was using this, now I need to go explain to my boss what it was I did. And they came up with an explanation. That's my view of it. Yes, okay. So we'll stop here, and then we'll see more clustering next Wednesday. Homework is due on Wednesday before class. The TA has office hours today and tomorrow because the homework is due this week, and most of you haven't done most of it yet. So